Alright, here we go with iChem lesson 24 and exchanging heat from one sample to another. First I want to build off the idea of basic heat flow that we did in class today. Right, so in basic heat flow we know the equation is Q equals mc delta T. We can determine the final temperature of a sample of 75 grams of water if it begins at 20 degrees and gains a certain amount of energy. These are just plugging in Q. This is T initial. This is the mass, and we know the specific heat of water equals 4.184, or just 4.18 is fine, joules per gram degree Celsius. Okay, so we know all the pieces and we can plug them in. What's different about heat exchange is you take now, and a lot of our examples will involve something like this. You take, say, a block of heated iron and drop that into the water. That energy, that 784 joules potentially, are coming from the iron. So iron is going to lose energy and water is going to gain that energy. They're exchanging heat between each other. So the temperature of the iron is going to go down and the temperature of the water is going to go up, and the final temperature of each of the two things will be equal after they exchange the heat. Now, comparing basic heat flow to heat exchange, basic heat flow involves one substance. Heat exchange involves two substances. The basic equation for when two substances are involved is Q lost plus Q gained equals 0. Now, it's important that we recognize our assumption that no heat is lost to the surroundings. This idea is called calorimetry. It's best performed in some sort of insulated environment to ensure that this quality is true, that no heat is lost to the surroundings. So let's do an example calculation. Same one from the other side. We now have a 25 gram sample of pure iron starting at 85 degrees, and it's dropped into a 75 gram sample of water that's initially at 20 degrees, and you want to know the final temperature of that water iron mixture. Excuse me. Okay, so let's go through first and identify some of our things. In these cases, you'll be given two masses. This first one we'll call MF, the mass of iron. I'm saying F because iron is Fe. And here we have MW, the mass of water. You're also given the initial temperature. This is the Ti of iron. And here we have Ti, let's just say W for water. And what you're looking for is TF, the final temperature. This is the final temperature of both the iron and the water. They'll be the same temperature. Remember our equation, Q lost plus Q gained equals 0. Well, the first step is deciding which one's going to gain and which one is going to lose. So the one that is losing energy, well, that's definitely iron, because it's starting at the higher temperature. Energy always goes from hot to cold. So the hottest thing is going to lose energy, and what's going to gain energy is water. Now what we need to do is take this Q lost plus Q gained and the fact that we know Q equals mc delta T and plug it all into the Q lost equals Q plus Q gained equation. So we're plugging in our knowns. So Q lost is what I'm doing first. That means everything I plug into this Q equals MC delta T equation, I'm doing Q of iron plus Q of all the information of water equals 0. So if I plug all of this in, the first Q using this equation will be M of iron, which is 25 grams, times C of iron, which is given as 0.45 joules per gram degree Celsius, times delta T of iron. Remember, delta T equals TF minus TI. In this case, TF is my unknown, and TI I do know. So I'm going to put TF in as a variable. And TI is the initial temperature of iron, which is 85 degrees. I'm going to do all the same for water. Plugging in the mass of water, 75 grams. The specific heat of water, 4.18 joules per gram degree Celsius. TF again is my unknown, minus T initial of water, which is 20 degrees Celsius, and this is all equal to 0. Now I want to start simplifying. So the first thing I'm going to do is distribute. So I'm going to simplify by multiplying these two things together. So 25 times 0.45 is 11.25. And then just keep everything else in parentheses. We'll worry about that in a minute. Oops, times 85. And then plus 75 times 4.18 is 313.8. And then keep everything in parentheses still. We're going to distribute in our next step. Equals 0. And now distribute. This 11.25 distributes to TF and to 85. So first I have 11.25 times TF. Can't really do anything there. TF is a variable. Minus 11.25 times 85, which is 956.25. I'm going to do the same to the next set of terms. 313.8 times TF is just 313.8 times TF. And then 313.8 times now 20 is 6276. And then this is still equal to 0. Now my next step is going to be to combine like terms. So everything with a TF in it, I'm going to combine, add them together. So 11.25 plus 13.8 is 325.05, and TF stays there with it. And then I'm going to combine my other like terms. 956.25 and 6,276. Notice I carried over this negative. I'm just going to add these two numbers together, and I get 7,232.25. And this is all equal to 0. The rest is just algebra. I'm going to solve for TF. So the first thing I need to do is to get rid of this 7,232, I need to add it to both sides. And over here as well. So I end up with 325.05 times TF equals 7,232.25. The last step to solve for TF will be to divide both sides by 325.05. Over here, that cancels this out. I have to do the same thing on this side. So then TF, I'm running out of space here, but TF equals 7,232.25 divided by 325.05. And I end up with TF equals 22.25 degrees Celsius. This is the hardest of all heat exchange problems that you might have. Okay, so this one I'm solving for TF, which notice appears in this one and in this one. In other cases, if I measure TF, say, because remember temperature is measurable, whereas specific heat is not, you can imagine that this kind of calculation can be used to find specific heat. And we're actually going to do that in a virtual lab tomorrow. Also, this kind of calculation can be used to find the heat of reaction. If we can measure the temperature change, the heat gained by water, and that water is heated by the heat that is left off by a reaction, then we can measure heat of reaction. This heat exchange is really the connection to all of the chemistry-based calculations we would need to do. Now, don't forget to go do your Google form. If you're doing this for homework, this is not what you do. Just go to the Google form under homework. This is if we had time to get to this in class today. Some of you we did, some of you we didn't.